Let's pull up Paint. And let's get started. Okay, so number 43, see if my pen works any better today, is, so this is number 43 in 5-1. Okay, so we have 1 plus the cosine of theta, try switching with, just draw this way, divided by the sine of theta, plus the sine of theta, divided by 1 plus the cosine of theta. And that is supposed to equal 2 times the secant of theta. All right, so in these problems, it says verify the identity graphically, that would be easy. Verify the identity algebraically. Use the table feature of a graphing utility to check your result numerically. So that's the easy part, right? If we get to graph it or use the table feature, that's what makes it easy. But what we want to do is we want to tackle one side of the equation to make it look like the other side of the equation. So we're going to tackle the hard side of the equation, and we're going to try to make it look like basically we're going to tackle the left side and try to make it look like the right side. All right, so on the right side, we know that that over there is the 2 times the secant of theta, which is the secant is 1 over the cosine. So I think we're going to keep it in the sine and cosine value. Oh, it is. Thank you. That would be bad if we got to the end of the problem. I'm looking at 42 and 43. Yes. So now it's 1 over the 1 over the cosecant. So it's basically, sorry, I just said that wrong. It's 2 times the cosecant, which is the same as 2 times 1 over the sine. Thank you for pointing that out, Sarah. That would be bad. Okay, so let's look at this. What do I have going on my left-hand side? I got a whole lot of fractions with some trig functions in it. That's looking kind of fun, right? So my first instinct when it comes to these fractions is to make my numerators the same so that I can combine my 2 fractions together. All right, so we're going to do that in order to have a common denominator. I'm talking wrong. I just said numerator. Denominator is the same. You guys get me for my 9 a.m. before I've woken up. I want to make my denominators the same, right? So that I can add the 2 fractions together, basic fractions 101. In order to do that, I have a sine of theta in the denominator 1 and 1 plus the cosine of theta. It's not like there's this like term, so I'm just going to use the trick where I multiply the first fraction by the denominator of the second fraction by the denominator of the first. Okay, so maybe writing I'll be better than speaking my words here. So I have 1 plus the cosine of theta over the sine of theta. And then in order to get a like denominator, I'm going to multiply this by 1 plus the cosine of theta over 1 plus the cosine of theta. So that's just like multiplying by 1. We're allowed to do that, right? And we are going to end up with the same denominators. All right, second term, we have sine of theta over 1 plus the cosine of theta. This one's a little bit easier. It doesn't look as painful to multiply by. So in order to get the same denominator, I am going to multiply by the sine of theta over the sine of theta. I'm just going to leave my other side of the equal sign up there as we work through this. This looks kind of ugh, right? the one thing that I am kind of keeping in the back of my mind as I start to work through this is that I know that I have the Pythagorean identities where I have sine squared of theta plus cosine squared of theta equals 1. So I'm hoping that somehow in all this, I end up with the Pythagorean identity, and then I can simplify that way. It's kind of in my brain where I'm hoping that we get to, but we'll see. Okay, so let's do some simplifying here. So when I simplify my first fraction over here, right, the denominator becomes sine theta times 1 plus cosine theta. That's good. The numerator, I have two binomials multiplying by each other, right? I have 1 plus the cosine of theta times 1 plus the cosine of theta. So I'm going to have to bust out my FOIL skills in order to multiply the two binomials together, right? So I have first, which is 1 times 1. So you can also FOIL trig functions. 1 times 1 is my first term. My outside term is 1 times the cosine of theta, so plus the cosine of theta. My inside term is 1 times the cosine of theta, so of theta. It's going to get worse before it gets better at doing these, right? And then my last term is the cosine of theta times the cosine of theta, which is the cosine of theta squared. Okay, and then my second fraction, I have, again, sine of theta, 1 plus cosine theta, and I have a sine squared theta. So the thing I like about having the sine squared of theta and the cosine squared of theta is that in my head, I'm like, yay, I can use the Pythagorean identity. So it looks like I'm going to be able to use that. All right, so next up, we're going to combine our fractions together and also make my paper longer because I'm going to need a lot more room, right? So we get 1 plus cosine, actually, we have cosine of theta plus cosine of theta, so that would be 2 cosine theta, right? Plus cosine squared theta plus sine squared theta. And we'll just leave everything that's on the bottom kind of there. The sine of theta over 1 plus cosine theta, right? All right, so this is where I was hoping this would work out. I know that the sine squared of theta plus the cosine squared of theta equals, if you go back to your identities, sine squared of theta plus cosine squared of theta equals 1. So I'm going to use that identity, and instead of this big cosine squared, sine squared, I'm going to insert a 1 here. Keep extending my paper because we've got some work to do, right? Everybody following along okay so far? Still with me? All right. So we got 1 plus 2 cosine theta plus 1. Good. You guys are all here. Over sine theta 1 plus cosine theta. And I'm going to, so you don't have to painfully watch me write, I'm just going to go ahead and add this 1 and the 1 together by the power of technology. And I'm going to make this plus 2, just so you don't have to watch me rewrite it over and over again. All right, so I have this pesky little, I have this pesky little 1 plus cosine theta in the denominator, right? And I also have 2 cosine theta plus 2 in the numerator. So if I pull 2 out of that, I'm left over with cosine theta plus 1 over the sine of theta, 1 plus the cosine of theta. That's convenient, right? Because I have I have the 1 plus the cosine of theta in the numerator and the denominator, I can go ahead and cross those off, which makes me really happy. And I'm left with 2 divided by the sine of theta, which thankfully Sarah pointed out I am trying to get to the cosecant, which is 1 over the sine. So I get 2 over the sine of theta is equal to 2 over the cosecant of theta. Ta-da! So that's how you do those problems. So it's actually good that you asked that one, Sarah, because that's the kind of problems that I wanted to show you. Sure. Did that make sense, guys? I mean, it's not, I feel like this section is, it's kind of like a puzzle, and that you have to kind of figure out what, what works to simplify your functions, but it's also not, it's not any new information. You're just going to be using those identities over and over again. So, and again, just a reminder, when you're doing this, all of them, 27 through 44, they say use a table feature to check your result, which is completely great, right? I don't expect you to print out your table function. So you can just go into Desmos, your graphing calculator, well, I'll just show you really fast since we have it here. Aiden, I'm laughing at your comment. That's why I chuckled in the middle. Yes, that is true. When you're actually doing it, sometimes you're like, whoa. Would you like to see, well, I'm pulling this up for the table function. Would you like to see another example from this section or continue on? All right. Got 2 goods. You can always try it too, and then if you have questions, that's all right too. So all I'm doing here is I am attempting to correctly graph my function. It helps if you write it correctly, right? So 1 plus the sine of theta x7, and that equals 2 times the cosecant of. All right, so when they say check it, again, just check it on your own. You don't need to write that all out for me. You could see when I was typing it in that these 2 graphs overlay each other, so you know that they're the same. But if you wanted to use a table function, then you're just going to go in and convert each side of your equation to a table. If my calculator can, there we go. So you can see that the values are consistent. Either way, table, graph, that all works. Okay, so 5.2, the good news is a very easy, quick little section. The homework is 1 through 9 odd, and the examples are, I think, pretty easy peasy. I don't know. I know I struggle with, it's slightly different than 5.1, but not much different. So basically what this is called verifying trigonometric identities. Let me pull up my notes here. I actually think the steps for how to verify trigonometric identities is funny because you don't usually hear this in a math book. So you'll see step 1 says, work with one side of the equation at a time. It is often better to work with the more complicated side first. So I think we all know that Like if we were going to verify this identity down here, we need to work on the left-hand side because there's not a whole lot we can do with the number 1, right? Number 2, look for opportunities to factor, add fractions, square a binomial, or create a monomial denominator. So that's kind of what we were already doing, right? And that number 43 that we just did, we had to, we had to make like denominators. We had to, do all kinds of different things. Anyway, look for opportunities to use fundamental identities. So that's what we were looking for. We were hoping that we could use the Pythagorean identity, right? And they say sines and cosines pair up well, as do secants and tangents, and cosecants and cotangents. So they're good friends, those sines and cosines, tangents, and secants and cosecants and cotangents. So the reason that they said that is if you look back to a couple pages ago, when you look at your fundamental identities, we have the Pythagorean identities, sine and cosines together, tangent and secant is together, and cotangent and cosecant are together. Step 4, if all the preceding guidelines do not help, try converting all terms to sines and cosines. So I think that is a good tip. If you can get basically down to sine and cosine, then you can maybe see some ways that you can simplify terms or pull things out. I agree with that. And then step 5, always try something. Even making an attempt that leads to a dead end provides insight. So I just thought that was funny for a math book to have that listed out like that. But it's true. When you're in these kind of sections where you're kind of just looking at identities or expressions and you're trying to figure out, it's really just kind of a puzzle of, okay, how can I change what trig terms I have and use identities that I know to turn it into something else. So I don't know. I don't know why I thought that was funny. Maybe I'm just cheesy math jokes. I don't know. Just always try something. Okay, so this section actually is very easy though. So there's a couple identities here and we're doing what we did in 43, but they're just calling these identities because, for example, number 2, the secant of y times the cosine of y equals 1. That would be an identity because you kind of know right off the bat, right, that the secant of y is 1 over the cosine. So it makes sense that if you take the reciprocal times the value, then you're going to get 1. So that's why this section's a little different, just more in nomenclature than anything else. So what we're going to be doing is the same thing that we did. We're going to take our equations. We're going to try to show that they are equal to each other. So for example, this will be a quick, easy section for you guys. So number 2, we don't even really have to write all that much out for it. So number 2, we have the secant of y times the cosine of y equals 1. So if we wanted to verify the identity, we would just say, oh, well, the secant of y, another way that we can express that is 1 over the cosine of y times the cosine of y, right, equals 1. And we know that 1 over the cosine of y times the cosine of y is 1. So 1 equals 1. Just kind of as simple as that, right? If all the problems were like that, wouldn't that be wonderful? But they're actually not too bad. So let's just kind of go through these because it's going to really take us not a whole lot of time at all. So number 4, for example, a little bit more complicated, but not too bad. We have the sine squared of t over the tangent squared of t equals the cosine squared of t. Okay, so sine squared of t, tangent squared of t equals the cosine squared of t. So in this case, I'm going to use, I forget what it is, step 4? No, 3, 4. I'm going to use the fact that I have sine and cosine and tangent in here. And if I convert my tangent to sine and cosine, then maybe some things are going to cancel out easily for me. All right, so I'm going to leave my sine squared alone. Sine squared of t. I'll leave that alone. I'm going to break my fraction up. So I'm just going to, put that over 1 just to be really clear. And then on my denominator, I have the tangent squared of t, right? I feel like I'll just write tangent squared of t. I know that the tangent, just the straight tangent, not when it's in the denominator, is the sine over the cosine. So when my tangent is in the denominator, right, it's just going to be flipped. So another way of writing the tangent squared of t would be, and this is obviously also equivalent to the cotangent, but we could also write this as the sine squared of t over the cosine squared of t. So this is how the second fraction is how I'm rewriting 1 over the tangent squared of t. And then obviously we have our other side. So what's nice about this, when I rewrite the tangent as a ratio of sine and cosine, you see the sine squared of t in the numerator crosses the sine squared of t in the denominator, and I end up with cosine squared of t. All right. Number 6. So I think you could probably fly through this section because it's pretty. After you've done the ones in 5-1, I think this one will be easy. I don't know what I clicked on. There we go. Okay, number 6, we have the cosine squared of beta. We decided that's what it was, right, Adam? The cosine squared of beta minus the sine squared of beta equals 2 times the cosine squared of beta minus 1. Okay, so my first thing in my head that's like ding, ding, ding is I'm really hoping to use the Pythagorean identity, right? Because sine squared of beta plus cosine squared of beta equals 1. So I'm really hoping that that works out for me here. Where do I want to put this at? Scroll down a little. All right, so we've got cosine squared of beta minus sine squared of beta equals 2 cosine squared of beta minus 1, right? Okay, so I should probably get everything on one side of the equation, right? Let's see. I know doing this I'm going to end up with some negatives, but that's all right. I'm going to subtract 2 cosine squared of beta from both sides. Okay, so I end up with negative cosine squared of beta minus sine squared of beta equals negative 1. So then I just have a whole bunch of negatives, but I know that I can multiply by negative 1, however you want to do that, and change them all to positive. And then this is just, this is the Pythagorean identity, right? We know that the sine squared of beta plus the cosine squared of beta is 1. So we just say it equals 1. So that's really it for that. I can do 8 and 10 for you. I don't think that it's going to add a whole lot of value. They're going to use the other identities. Just kind of a reinforcement of 5-1. So you can kind of just think of that as continuing on for that. Any questions? Seems pretty easy. Just 1 through 9, so not too bad. You guys want to try number 9? Let's try number 9. So you try, I'll give you, I'll write it up on here. If you have paper near you, try it out. Because as Aiden says, sometimes when you do something, it's not the same as watching someone do it. So I'll write it here. I'll give you like a minute or 2 to start. Solve it together. So this is number 9 and 5-2 from your homework. So Okay, there we go. So try number 9. I'll give you like 2-3 minutes, and then we'll do it together. All right, Aiden's done. He's doing a speed identity verification. All right, you guys rock. So if you got it, probably don't even need me to do it, right? So did everyone use their friend foil, right? 1, and then when we foil the outside and the inside, they cancel out, right? Because it's negative sine of x plus the positive sine of x. So we end up 1 minus sine squared of x. I'm paraphrasing since you guys all completed it so quickly. 1 minus the sine of x equals the cosine of x. If we add sine of x to both sides, we get 1 equals the sine of x squared plus the cosine of x squared. And that's our good old Pythagorean identity once again, which shows 1 equals 1. Ta-da! Easy peasy. We like this section, right? If only everything could be 5 too. Actually, a lot of them are very similar, so awesome. Awesome, awesome. All right, so we'll start a little bit into 5.3. Honestly, we probably won't finish it. Another note on your homework as I'm going through things. I'm changing the 5.3 homework to just 1 through 39 odd. So make sure you write that down. Unless you want to do a little extra, you're welcome to. So zoom in a little. There we go. We'll cross this off here so you can, so it's official 1 through 39 on. There we go. Yep, 1 through 39 on. Okay, so in 5.3, again, I don't think we'll get through the whole thing. That's okay. We can pick up on Monday. We're solving trig equations. So it's kind of the same thing again. It's a different variation on what we've been doing. Our good friend, the unit circle, is going to come back into play. So bust out your unit circles again. I didn't post one on here, but I can send one out again if you'd like. The first little part is basically, it says we're going to verify that a value is an x value is a solution to an equation. So this is very easy stuff. Basically, you're plugging in your x value to an equation and you're seeing if it's true or not. So if you get to your homework and you get stuck on that, let me know, but I think you guys can all do that. It's basically just showing the difference between this and what we've done in the past is that you can see that our equations that we're using are a little bit more complex. We've got, secant to the 4th power minus 1 or 3 times secant squared of x minus 4. So you just get a little bit more complicated of equations. So really the point of this is just to be comfortable plugging in to a higher value equation and proving that it's true. All of these are solutions, so you're just basically verifying that. So then we kind of get into a little bit more interesting stuff that we're working on, which is in 7 through 24, where we're finding all the solutions to an equation. Okay, so we talked a little bit about this at the end of chapter 4, and we talked about using the inverse function to do some of these, but we're going to talk about a couple different methods for how we can solve solutions to these equations. So just like an algebraic solution, there's multiple ways to find, an algebraic solution. When we have a trig equation, there's multiple ways to get to the answer. So what do I mean by that? All right, so number 8 here, we have that the cosine of x equals the square root of 3 over 2. And in 8 through 12 or 7 through 12, what they're asking is for us to find all the solutions to the equation in the interval 0 degrees to 360 degrees. So they've thrown us off a little bit because we're back to degrees. We were all in radians, right? And so they're asking for basically solve for x, right? Give all the solutions from 0 to 360 degrees. And that's pretty much it. So there are more than one way to solve this equation, right? So one way is this is just a basic cosine of x, right? Square root of 3 over 2. One option is that we can find our friend unit circle, and I don't have a unit circle up here. If I search unit circle, I'm sure that there'll be a plethora of unit circles. Sure, that one will work. Okay, so we know, excuse me, maybe, if I can get it to be big enough for us. I just want a big unit circle to look at. There we go. Okay, so the problem was the cosine of x equals the square root of 2, right? You remember that, bust out your from before break. The cosine, just a really quick review, because I can't even draw on here. Okay, so you'll remember that the cosine value, like if we draw, oh, I just did that wrong. We draw our coordinates here, right? This is our x and our y. If you think about cosine, cosine represents the adjacent side over the hypotenuse. So the cosine represents our x value, right? So we want to look for x values that match the square root of 3 over 2. So it looks like when x is 30 degrees, the cosine of 30 degrees is square root of 3 over 2, right? And we also have, as I work my way around the unit circle and I'm looking at my x values, I also have a value down here in my 4th quadrant, right? That at 330 degrees, the cosine of 330 degrees is also the square root of 3 over 2. So that's one possibility. Look at your unit circle, one that has degrees on it in this case, and determine, where your sine or cosine value is true, and then those are the two solutions to your equation. So I go back here. I know that x is true at 30 degrees and also at 300 degrees. $330, sorry. Okay, one option. Another option, just like, I mean, this is what we're doing is we're solving equations, right? Another option is graphing it. That's always an option, right? When you have two sides of the equation and you want to figure out when they're equal, you can always graph it and see when both are true. So if I go to Desmos, I'll make it a little smaller here so we can see. Okay, so one side of my equation is my cosine of x, not c, it's cosine of x. Got our nice curve there, right? And we want to know, when does the cosine of x equal square root of 3 over 2? And I have to also remember that Desmos is automatically in radians, and I'm working in degrees. If you're Aiden's calculator, you're starting in degrees, and you have to remember to turn it the other way, right? So that means that my x-axis right now is in radians. So I want to go from 0 to like 360 degrees because that's what my range is going to be. Zoom out a little bit there. Okay, so let's maybe make this from, so we can see a little better. Let's make this from -2 to 2. There we go. That looks more like a cosine curve, right? So this is just like you've done with other equations. I think most of you have probably done this before. You see, this is my y value. My one side of the equation is square root of 3 over 2, which is represented by the blue line. The red line represents my cosine curve. So I know that one possible solution is when x equals 30. And another possible solution is when x equals this 330 degrees, right? There are more solutions than that, you can see, but we're just looking over the interval between 0 and 360 degrees. So 390 degrees is also a solution, but we don't have to include it in this set. So that's another way that we could find the solution. There is yet another way. I know everyone loves it when there's more than one way, right? So another way would be to graph and find the intersects. No, I'm just going to leave it there, intersections. Okay, another way would be that we can use the inverse cosine, which is what we have learned right at the end of chapter 4, right? So if we have the cosine of x equals the square root of 3 over 2, we could say the inverse cosine of the cosine of x equals the inverse cosine of the square root of 3 over 2. Okay, so that leaves us with the inverse of the cosine is just x. And then if we evaluate the inverse cosine of the square root of 3 over 2, let's see what happens with that. Where are you, Desmos? There we go. So we want the inverse cosine of the square root of 3 over 2. So you see that the inverse cosine of square root of 3 over 2 is 30, which is one of our solutions. The downside of this is that it does not give you all the other solutions to it. So it does give you one of the values, but if they're looking over a certain range, then you're going to have to add some additional information in to get the other values. Okay, so those are three options to do the same thing. You can see 7 through 12, it's just using sine, cosine, tangent, just different varieties of the same thing. So you can graph, you can unit circle, You can use the inverse. All of those are options in order to figure out what the values are. Okay, so how did that feel? Not too crazy, right? Just pulling out that old information of the unit circle. Nice. I like it. I like it, Jennifer. So 14 through 20, what are they? 24. 13 through 24. Same exact thing, except instead of degrees, which now feels weird to work in degrees, right? We're going to work in radians. Back to radians. So we're going to find over the interval of 0 to 2 pi. I don't even know if you want to see one of these. I'm just looking to see if there's one that looks kind of complicated. They all look pretty straightforward to me. I mean, even like number 22, the secant of x equals 2. Okay. You can just graph the secant of x and 2 and find out where they intersect. That's a pretty easy thing to do. All right. So 25 through 34. Try to make it look a little bit more complicated, but it really is just a matter of changing your equation, moving your equation to make it in a format that makes it look more easy. So what do I mean by that? Oh, got a nice red border. That's not what I meant to do. Okay. That's what I'm trying to do. So for example, let's go right to like number 30. Okay. So 30 says we have 3 times the cotangent squared of x minus 1 equals 0. They're asking us to solve the equation. Okay. So just like anytime you're solving an equation, right? Our ultimate goal is to get x by itself so that we can figure out what x is. We're going to do all the same things that we would do to a regular equation that we do to a trig equation, right? We're going to try to get everything away from our x term so that we can solve it. So what I mean by that is, we're going to add 1 to both sides. So we get 3 cotangent squared of x equals 1. Then we're going to divide both sides by 3. Okay, so we have the cotangent squared of x equals 1/3. Okay, we want to get x by itself as much as possible. So since we have a squared term on the left side, let's go ahead and take the square root of both sides. Okay, the one thing about taking the square root is don't forget that we want the plus and the minus, the plus or minus, right? So we have the cotangent of x equals plus or minus the square root of 3. So now we're back to the same situation when we were back to solving number 8. We have multiple ways that we can try to solve this equation. The easiest way is obviously going to be graphing, right? So we can graph the cotangent of x on one side and graph plus or minus the square root of 3 on the other side. So let's just do that to get a baseline of what we're talking about. So we have the cotangent of x on one side of the equation, and we have, I don't know if it lets me do plus or minus. Nope. So we'll have to do square root of 1/3. And in order to get it to graph it, you need to make y equals, right? And we also need a square root of 1/3 equals y in the negative. And then I notice that when I'm looking at my graph here, I'm still in degrees. So after you do basically 7 through 12, go back to radians, right? And then my axis is all crazy. So we're going to go 1, 0 to maybe 2 pi. And we'll step by pi. And let's see how our graph looks. Okay. So I have my graph. There is, here is my cotangent curve in green, right? So the values where my equation equals the positive square root of 1/3 are at pi over 3 and 4 pi over 3. And where it equals negative square root of 1/3 is 2 pi over 3 and 5 pi over 3. Okay, so my solutions would be x equals, I just lost them when I was over there. I think I have them written down. I've got x equals pi over 3 and 4 pi over 3 and 2 pi over 3 and 5 pi over 3. That's crazy pi, but you guys get the idea. Okay, 5 pi over 3. It's supposed to be pi there. So those are solutions to my equation. We could, if you wanted to, if you didn't want to do graphically, you could use table function. That I didn't mention that, but you can also use table function. Another option would be to use the unit circle in this case. It would be a little more complicated. What I would recommend doing is, since this is the cotangent of x and we have 1 over 3, I would probably flip it to make it the tangent of x equals the plus or minus square root of 3. And then you can look around the unit circle and find where does the sine divided by the cosine equal plus or minus square root of 3. Did that just make sense what I was saying there? So what I was saying is that if you wanted to use the unit circle, instead of writing this cotangent of x equals plus or minus the square root of 1 over 3, I would rewrite this as tangent of x plus or minus the square root of 3. Okay, and so then when I go to my unit circle, I am looking for values where the sine divided by the cosine equals either positive square root of 3 or negative square root of 3. So if I go to a unit circle, maybe make it a little smaller so I can do both at once. I'm running out of room. All right, so I want to find the values, right, where the sine divided by the cosine equals the square root of 3, positive or negative. So if I divide, I need a different color. I'll do blue. Oh no. Here we go. Purple, there we go, that'll work. So the square root of 3 over 2 divided by 1/2 will give me just the square root of 3. So 1/3 is a possible value for my tangent, right? Over here, I have square root of 3 over 2 divided by negative 1/2 will also give me negative square root of 3. So this is another possible solution. We got right here, right, which is 7 pi over 6, which we didn't actually mark down yet. And we have, oh, we have multiple values, don't we? I missed right here. No. Yeah, this value will work too, and this value will work too, right? So we have multiple values that will work to make our tangent work. Yes, so we have multiple ways that we can find that. The other thing to note with this is that you'll notice once we get to 25, they say solve the equation, and it's no longer over a particular interval. Okay, so let's go back to our graph. Is everybody still with me? We're almost done, I promise. Okay, so last little thing I want to show you. For number 24 and above, you'll notice when I go back to my graph, there's many solutions to my equation, right? It's over multiple, like it keeps going on for forever and ever. So when I look at this first solution, pi over 3, and then the next one is 4 pi over 3, and then we have 7 pi over 3, you'll notice that we are going up by interval of, well, from here to here, we're going up by interval of 2 pi. So the way that we actually indicate this when we have more than one solution, when we're writing out our solutions, is that instead of sitting there and writing out all the possible values because it keep going on forever and ever, is that we can say, and I know that it's a total mess here, that x equals pi over 3, and then we say plus 2 pi times some number n, which represents the interval. And actually, in this case, since we can look at it and see so clearly, the interval is actually just pi between them, right? Because to get from 3 or pi over 3 to 4 pi over 3, we're just adding the interval of pi. So if we really want to be, so in general, you can use the n term. That will kind of be the catch-all here. If we really want to be specific for this, we could just say pi over 3 plus pi times some number n, where n represents a whole number. So you can have it 1 pi away, 2 pi's away. It will basically catch all of the other solutions. And I'm sorry that this is such a mess, but this is when we're not talking about a specific interval, that's how we would indicate that it's repeating over that time. And then on the negative side, right, if we go back to Desmos, on the negative side, we have 2 pi over 3, and then it repeats again at another interval of pi. So we can say x equals 2 pi over 3 plus pi times some interval. So that's the last little tricky part to that. Okay, guys, that's it for today. A whole 2 minutes early. I thought we were going to get it done early, but always, right? So I get to see you guys on Monday. We will continue on with chapter 5. Thank you guys for joining. Try out some of those. Let me know if you have any questions. And yeah, thanks for coming. Have a great day. Have a great weekend. Thanks, guys. Thank you so much. Have a good day. Bye.